Hello, so we're going to be going through the second part of Thermo Practice number 4. So we're problems, 11 through 14. So if we look at problem number 11, we're asked to find the value of delta G. And in the earlier problems, we've found delta G using our equation delta G equals, H minus T delta S. But it looks like in this problem, we aren't given any values for H or T or S. So what we should be using in this problem is this other equation right here, where delta G equals the G of formation of products minus the G of formation of reactants. This looks very similar to the equation that we're familiar with at this point about finding delta H using the heats of formation of our products and reactants. So, yeah, again, delta G of formation, it's pretty similar to that other thing we talked about, heat of formation. Notice that if a substance is already in its elemental state, like hydrogen gas or nitrogen gas, the G of formation is 0 because the delta G of formation is defined similarly to the heat of formation. It is the change in free energy associated with forming 1 mole of something from its substances in their standard states. So if it's already in its standard state, its delta G is 0. So the delta G for this reaction is the G of our products minus reactants. So nitrogen is one of our products, it is 0. Our other product is water vapor, and there's 2 of them, so I'm going to multiply that by 2, and then I'm going to subtract my reactants. One of them is hydrogen, it's in its standard state, so that's 0, and then I have 2 nitrogen monoxide, so that looks like that. So our delta G ends up being negative 632, and our units here are in kilojoules per mole. So that is part A. Part B, is it thermodynamically favorable? Yes, and our justification is because it is a negative delta G. That is all we are being asked in that scenario, is what is the sign of G? Predict the sign of delta S for this reaction. Justify your answer. Well, let's look at this reaction. On the left, we have 4 moles of gas, and on the right, we have 3 moles of gas. So state of matter stays the same, but I'm decreasing my moles, so I have less disorder, so it is a negative delta S value there. So thinking about delta H, what is the sign of delta H? Do they give us any info about H? Not really. So we have to think, what do we know? We know the sign of G, we know the sign of S, and we know an equation that relates those things. So delta G equals delta H minus T delta S. I know that G is a negative, and I know that S is negative. So the question is, what is this thing right here? Okay. So if we think about our possibilities, let's see, if H were positive, so if you had a positive delta H, then you would have a positive value minus a negative value, and that would always give you something that is positive. Okay, but we know that G is negative, so it must not be positive. So what if delta H were negative? Then you could have a negative minus a negative, and that could sometimes end up being positive or negative based on like how big these numbers are, right? So if it was like negative 10 minus negative 100, this would give you a positive value, but if it was negative 100 minus negative 10, that would give you a negative value. So it's got to be that H is negative, because again, why? If I go back, if H were positive, then G would always be positive, and I know that G must be negative. So H must be negative. This is the kind of thinking you want to apply with this equation right here. And if it helps you, plug in some numbers, okay? So like going up here to this scenario, like what if H were positive? If I had, positive 10, and, you would always end up with a positive value no matter what numbers you plug in. So that's what that question's getting at there. So let's look at 13. Sign of delta S. Everything's a gas. I'm just going from 3 moles of gas to 2 moles of gas. So I have fewer moles of gas bumping around, so there's less disorder, so it is a negative delta S. Does the change in entropy favor reactants or products? So having more entropy is kind of like favorable in the universe. So the entropy is going to favor the side with more disorder. So the change in entropy favors reactants. Okay, so the reactants have more disorder. Another way to think of it is, since the delta S is negative, that does not favor the forward reaction. Okay, that does not contribute to the forward reaction being spontaneous. All right. Delta G is negative at low temperatures and positive at high temperatures, so what must the sign of delta H be? So we're going to do more of this reasoning like we just did, using that equation relating G and H and S. Sorry, everything just got shuffled around. Okay, we will make it back down. So we want to think through our scenarios here. Okay, so here's our equation. Delta G equals delta H minus T delta S. I already know that S is negative from part B and A. And I know that G can sometimes be positive and sometimes be negative. So the question is, what is the sign of delta H? So if delta H were positive, I would end up with a positive number minus a negative number, and that would always be positive. If H were negative, I'd end up with a negative number minus a negative number, and this could be positive or negative depending on the values. Okay, and we are told that delta G is sometimes negative and sometimes positive, therefore our delta H value must be negative. So under what conditions does this process become thermodynamically favored? That means under what conditions does G become negative? And it just told us right here it is negative at low temperatures. So at low temperatures, you end up with a negative delta G. So that means that the process will be favored at low temperatures. All right, last problem. If you look at 14, sign of delta S. So I'm going from 1 mole of a solid to 3 moles of a solid. So notice that moles is not conserved, right? Number of atoms is conserved. So we still have 2 atoms of copper on the left, 2 atoms of copper on the right, 1 atom of copper on the left, 1 atom of sulfur on the left, 1 atom of sulfur on the right. So the atoms are conserved, but the moles are not conserved. The molecules are not necessarily conserved. So you could have those atoms arranged in different ways. So if those atoms are like broken up into more bits, that's going to be more disordered. So when you have an increase in number of moles of things, then it's going to increase your disorder. So this will be a positive delta S here. Does favor reactants or products? So in this case, the products are favored because the products have more disorder. And the delta G is positive at low temperatures, negative at high temperatures. What must the sign of delta H be? So again, we're back to this equation. Okay. I know in this case that S is positive. Okay. And I know that G, so I'm trying to figure out what the sign of H is, and I know that G can sometimes be positive, sometimes be negative. So let's again think through our scenarios. So if delta H were negative, then you'd have a negative number minus a positive number. So you'd have your delta G would always be negative. Okay. If delta H is positive, you'd have a positive number minus another positive number. So delta G could sometimes be positive or negative depending on how big these numbers were, right? So like if it was, 10 minus 90, then you'd end up with a negative number. If it was 90 minus 10, you'd end up with a positive number. So this scenario tells us delta G is sometimes positive, sometimes negative. So that means that it must be scenario 2 here. You must have a positive delta H for this reaction. And under what conditions is it thermodynamically favored? It's just basically saying, what would make this reaction have a negative delta G? And it tells us right here, delta G is negative at high temperatures. So it is going to be favorable at high temperatures. And again, we're talking about something being favorable. We're talking about having a negative delta G value. So that is it for thermo practice number 4. Thanks.